Tuning of a PID controller for optimal performance of ball and beam system. One of the challenging problems in control system design is control of nonlinear, unstable systems. Many of industrial processes possess such characteristics inherently, which makes it difficult to design a proper control strategy for them. These systems cannot be brought into laboratories to be studied in real time due to their physical dimensions and cost. There are many standard laboratory instruments like inverted pendulum, floating ball, quad rotors, which are both simple in construction and physical dimensions and exhibit same characteristics, ball and beam system being one of them. It is a special case of a second-order system and is double integrating type in nature. It thus proves to be a good arena to study different control strategies. PID controllers are widely used in industries for controlling such processes for long time now due to its simplicity and very few parameters to tune the system. Many tuning methods are proposed to tune the controller for optimal performance, the most common being the trial and error and the classical Ziegler Nicholas methods. Many researchers have contributed in elucidating the control problem of the ball and beam system. The physical layout of the system is presented in one which is based on Arduino board as controller and MATLAB for data acquisition in real time. The correlation study between theoretical and practical response of the ball and beam system is shown in 2. Tuning a controller is optimizing its tuning parameters for optimal system performance. Many researchers 3 to 4 have used the trial and error method along with Ziegler Nicholas method to tune the system for optimal performance within tolerable constraints. A new control strategy based on fuzzy logic has been proposed in 5.6, which presents hybrid fuzzy controller and model-based PID to address the problem. The fuzzy controller proves to be better at disturbance rejection and provides zero steady-state error. Results depict SMC, sliding mode controller and CDM, coefficient diagram method 7 to 8 show better performance in error elimination and set point tracking along with stability response and robustness of the system respectively. New EPID controller has been proposed 9. Here the results show that EPID eliminates the overshoot and decreases error by adding a feed-forward controller with proper design. In 10 Newtonian mechanics is used to derive the model of the system. In 11 Lagrange's method is used to derive the model of the system and suggest to have 2 degrees of freedom. The nonlinear model is derived using first principles and is linearized around the equilibrium to gain a state space model. 12. Reference 13 shows use of Lagrange's second type equation to model the system. The use of normal PD controller is done to regulate the nonlinear model in 14. In 15 SIMC-based PID and H-infinity methods are used to control the system. PID controller along with neural network and LQR control have been applied to control the system in 17. Reference 18 shows comparison between LQR subspace stabilization and combined error metric approaches. Various controllers exhibit characteristics which outperform PID in many aspects. But since PID controllers are being widely used in industries, they cannot be replaced. Although conventional PID achieve some performance measures, the other like ISE, ITAE, overshoot still needs to be improved. Therefore, besides these conventional PID tuning methods, there are many heuristic methods that can be applied for PID optimization, including the particle swarm, honeybee, ant colony, and genetic algorithm, which can overcome this problem. In 19 the controller tuning is done using SA and CSA heuristic tuning methods. GA and A algorithm are used to tune PID controller, and performance evaluation is done on basis of error criteria in 20, 27. Also in 21 meta-heuristic techniques like ABC have been used to tune the PID controller and compared against swarm optimization algorithm. Reference 22 shows use of GA to tune the PID controller, and the results are experimentally verified on a ball and beam setup using Quark platform. In 23 to 25 GA has been applied to control the ball and beam system, reverse osmosis plant and Stewart's platform. Reference 26 shows application of LQR to control the system, and LQR parameters are tuned using GA. This paper aims comparison between the conventional Ziegler Nicholas, SIMC, simple internal model control PID tuning methods and the evolutionary, GA, genetic algorithm technique based on the ITAE criteria. The rest of the paper is arranged as follows. Section 2 depicts mathematical model of the system. Section 3 shows the design of the PID controller. The comparison between ZN-PID, SIMC, GA, is done in Section 4. And Section 5 concludes the paper. The rotational force acting on the ball is given by equation 3. Where is the moment of inertia of the ball and is the angular velocity given by equation 4 and 5 respectively. Substituting equation 8 in equation 7 and taking Laplace transform, we get the transfer function of the system as x ball position on beam, angle of the servo arm. It is clear that the system transfer function is a special case of second-order system and is double integrating type in nature. The double integrating type process is a special case of a second-order system. Lot of PID controller tuning methods focus on SOPT and FOPT systems, but very less literature is available for double integrating type processes. The most common being the SIMC, Simple Internal Model Control. Skogestad and 16 have provided resulting PID settings for controlling a double integrating process, quoting the need of derivative action required to control the process. Table 3 shows the SIMC PID settings for a double integrating process. This procedure results in only one tuning parameter. The small values of give fast speed of response and good disturbance rejection, while greater values of favor stable and robust system. The value of closed loop time constant is constrained to the iterations carried out to find value of that provide good trade-off between speed of response and stability. Based on the results provide good system response. The corresponding optimum settings are used for further analysis. Evolutionary techniques are algorithms inspired by natural processes of evolution in nature. These are heuristic methods to solve a given problem statement and optimize it. This has led to discovery of many techniques for optimization and problem solving. Genetic algorithm is a search-based algorithm based on principles of natural selection and theory of evolution, first introduced by J. Holland in 1970. The use of evolutionary techniques since then for PID tuning have been done extensively. In this paper, GA-based optimization tool in MATLAB is used for finding optimum PID settings. The procedure involves finding a fitness function that encompasses the iterations for desired result based on some criteria and run the optimization tool over the function. The process may take several minutes to hours based on complexity of the fitness function. The fitness function is designed on the criteria to optimize the IJERT performance criteria. Designing of the fitness function in MATLAB. Based on the results, the optimized PID settings obtained are. In this section, performance of the designed controllers are discussed. The simulations are carried out in MATLAB SIMULINK environment. The performance evaluation of the controllers is done by rating based on overshoot, settling time and peak response for closed loop response and set point changes and disturbance rejection respectively. The performance indices obtained for ZN-PID, SIMC and GA are tabulated as follows in Table 4, and Figure 5 to 7 show responses of the system for reference tracking set point change and disturbance rejection respectively.